Right, okay. Good morning. And so let's have a look at today's chart to start with, and it looks very like yesterday's. We're in this rather static situation at the moment. Here's this long front which was across the north of Britain yesterday. There's low pressure to the northwest of it, and then you've got high pressure away to the east. And we've got this run of moist southwesterly winds ahead of this cold front. So actually, weather today here in Manchester will be very similar to yesterday, so no great change. If we have a look at the rainfall again, that looks very, very similar. So this is rainfall this morning. Raining heavily in Scotland. These are sort of reddish colours, and Northern Ireland, but really not very much here in England and Wales. So we avoid all of that. And if I just flick it forward and you can see which way it's moving, you can see that there's a tendency for everything just to move along the line here. There's a point to be made about radar. If you look at this, it doesn't change at all. This bit over northern Scotland, northwest Scotland, it just stays the same colour. It seems as though the rain is moving through and leaving this the same. That's actually an artifact, okay? Yes, there are hills there, and yes, of course you get orographic enhancement of precipitation. You get more rain over hills. But the radars can't actually measure very well where there are hills, and so they add rain onto the measurement. So it's a little bit artificial. That always amazed me that you could actually pick out the Scottish coastline here. And thought, wow, that's really amazing that the rain follows the coastline. The rain doesn't follow the coastline. They've made it look as though it does. So, but still, it gives an impression of where the rain is. So, even though radars are very clever things, they're not particularly good at measuring the amount of rainfall. Quantitative precipitation forecasting, still a big challenge. That's the net. This is the Whitworth, and that tells the story really for the past 24 hours. This is wind speed here in the university, and very, very steady over the past 24 hours. As we see, no change in the weather chart. Steady wind of about 5 meters a second, and then you can see on the infrared. So this is the infrared, and again we've got the similar thing. Here's the front. So this is down looking at high cloud, and we've still got this thundery low. This is in the western Mediterranean. That's a thunderstorm. So you can see this sort of circular blob sort of growing over time, and these are all thunderstorms. These bright globular features in the infrared picture, these are big thunderstorms. So the atmosphere there is convectively unstable over because we've got this upper level low there. I'll show you that in a second. Over Ireland, so we show you the tephigram for Southwest Ireland. We don't want to forget about tephigams. What's the situation here in Ireland? Well, there is some. This is the infrared, and it's showing some upper level cloud. So the infrared is showing you high level cloud, it's not showing you the low level. If I wanted to see that, I would have to stop this from moving and switch over to visible. There we go. So this is looking at scattered sunlight, except it's determined to run through its sequence rather than stop. There we go. Stop. And you can see here in Southwest Ireland, there's actually quite a lot of sort of bright cloud, and so this is low cloud that you can see here. It's well lit because it's dawn. You can see shadows in these clouds here. So the tephigram for Southwest Ireland then, what does that look like? So and what do we make of it? It's so the red line is the temperature. So the temperature and the dew point match in this region here. They pretty well match here, and they're quite close all the way up the profile. This is a very moist profile in Southwest Ireland, and consistent with there being low cloud and high cloud observed on the satellite image. This was for midnight, satellite was for now, so obviously there's some change in time, but it's a very static situation, so not much change. Is it likely to give us deep convection? Well, clearly no, because this strong inversion here will prevent any convection from certainly from getting out to the boundary layer. In fact, any convection that's there is going to be fairly shallow. So we've got moist air here. It might just be a little bit of convection just in this lower part here. But in fact, the main boundary layer is pretty stable, as well as this inversion. So we wouldn't expect to see deep convection, indeed we don't, but we do see some high cloud. One point to make about these tephigrams, when you get up into the higher part of the atmosphere, the dew point becomes a rather nebulous concept, in that water doesn't exist in liquid form up in the upper troposphere. The clouds will be ice, right, because it's cold there. The temperature, so the temperature here, so this is minus 30, and this is minus 40 here. Okay, minus 10, minus 20, minus 30, minus 40. So this is minus 40. Well, at minus 40, you're only going to have ice. You're not going to have water. So we should be plotting the ice point here, and the ice point is a bit to the right of the dew point. So probably this air here is completely saturated with respect to ice, which is consistent with high cloud being seen here on the satellite image. If I switch over to the infrared again. Okay, so there's the high cloud. So the point of that is, yes, we've got a nice stable tephigram, but also we've got quite a saturated atmosphere, again consistent with this basic flow from the southwest. Okay, so I'm going to concentrate now on looking at the dynamics of the atmosphere. So obviously we're starting to move into the dynamics part of the course. And here's the canonical picture here. So here's our 500 millibar height. There's the temperature gradient across there. Here's the cold air to the north, warm air to the south. And here, just poking its nose into the picture here, is Tropical Storm Leslie, the thing that we saw yesterday. Now, here's to illustrate to you how unpredictable these things can be. Yesterday, when I ran the forecast forward, this thing found its way around to this region relative to the trough, and it grew into a large storm over the weekend. Okay? That's what I showed you yesterday. Now I'm going to show you the forecast from the same model 24 hours later. So this is from a model run from midnight last night. So we watch again. So as we go through, nothing much happens. We can see this trough forming, and then eventually this will start emerging. So this is Friday already. So it's coming across, but it's much later than yesterday's forecast suggested, and actually it just peters out in mid-Atlantic, and we no longer have this huge storm here. Okay, so that's a lesson there, is that you have to be careful when you use a model like this and try and use it to forecast the weather. You basically can't use a single model run to forecast the weather. Forecast centers don't. They run these models, they run maybe 50 copies of these models, all with slightly different initial conditions. And then they look and see how many of them, for example, would this find itself creating a storm. And that leads them to, well, that improves their confidence in whether the forecast is right or not. And of course, there are many different models. This one is called the GFS model. There's the ECMWF model, which is probably the most reliable, which is a European Centre model, and of course there are all the Met agencies have their own models as well, which is one included. But this is just an example today and yesterday of a nice example of how difficult it can be to predict certain features in the weather. Okay, so when you see doing all sorts of things like this, you know, this is the 24th of October. It's a bit of a flight of fancy, really, what it's going to do that far away. Here's something that's just a lead into some of the ideas that I'm going to be talking about in the course. This is from a model, Manunicast model, which is run here in Manchester, and this is a different model to the last one. It's a regional model, so it just runs this little box. The advantage of this model for me is that it gives me some more detailed graphics to play with. And what I'm showing you here is 300 millibars. Okay, so if I go to midnight last night, so this is 300 millibars from midnight last night. So these lines here, this is the height, 9460. So we can see that the chart is plotted using the height of a 300 millibar surface. And I'll be explaining in a minute why we're using height of a pressure surface rather than the pressure at, say, 9 kilometers, which we could equally do. There are little symbols on here that denote winds. Probably you can't see all that much from the back. But basically you should be able to see that these symbols very closely follow the ISO height lines on these charts. That's obviously the geostrophic relationship, and it's actually quite closely followed. Not uniquely closely followed, because there are parts of the plot where it seems as though the wind is slightly drifting away from these lines. And if I move it forward to sort of Wednesday, and again look at this sharp region of sharp curvature, it's fairly clear. If you look at the winds on the western side, they are definitely flowing across these lines in this region here. Although not here, it's following quite closely. Where there's sharp curvature, it's a little bit less so. So the winds are close to geostrophic at this level, but they're not perfectly geostrophic. And it's this departure from geostrophy that is going to be the important element of atmospheric dynamics, right? So I'm going to be talking about geostrophy really in the rest of this lecture. Okay, right? So that's the kind of weather for today, and so we'll start looking at this theory in a bit more detail. This is where I got to last time round. So this is the momentum equation, frame of reference fixed to the Earth, and we have this form of the equation. That's the pressure gradient term, Coriolis gravity, expressed as a scalar times a vector, and then this is friction, which is just denoted as F. We don't have formulae for that. We found that when we transform it to a local frame of reference, so that U always points to the east, V always points to the north, the U, V and W components, and D is the local vertical, the equation looks pretty similar. Here's acceleration, this time of the horizontal wind vector. U is the horizontal wind vector. Here's the same expression for pressure gradient. This is Coriolis, which becomes slightly more, slightly different form, but basically at the same time, the same term as that. Friction doesn't change. G doesn't come into the horizontal equation, so that's why it's not there. And then we have these extra terms here of order u squared, and A is the radius of the Earth. So K is a unit vertical vector. And then we also found that we've got this relationship. This u by dt here is the full differential, the Lagrangian differential, and in terms of the local rates of change, these partial derivatives, we have this advection term both for vectors and scalars. So that's what we did last time. What I'm now going to do is concentrate on these equations, but I'm going to look at them in component form. Okay, so this is. So what are these equations? Well, here it's the same equation. What I showed you last slide was a vector equation, and these are the components of the vector. So u is the eastward, northward, vertical component, and each equation separately written down here. So that's the pressure gradient term, clearly written like that in each case. The Coriolis term now starts to look rather simple. There was a cross product term, and all that means is that the v velocity term appears in the u momentum equation. That's what the cross product thing does for you. It rotates things through 90 degrees, and similarly here. It doesn't appear in the vertical. I've actually put the Coriolis force over here. This is the vertical component of the Coriolis, which doesn't really matter very much, but we'll show it. And then these are these u squared over a terms that I talked about. So again, uv over a. So if we, and that's the last time we're going to really see these. I just wanted you to see what they look like. So those are the full equations. If you actually wanted to write one of these models for forecasting the weather, you would be having to use those equations and write those. But we want to concentrate on understanding the large scale motions, these synoptic scale motions. And so we're going to conduct something called a scale analysis. In other words, we're going to estimate the size of all these terms in these equations using typical values that we know exist in the atmosphere. And this is a kind of standard technique for trying to decipher fluid motion, is to select the phenomenon that we want to look at and then try to basically throw away the terms in the equations that are small. That's a fairly standard approach to trying to understand physical equations. Okay, so what are these scales that we're interested in? Well, horizontal scale, obviously, 1,000 kilometers, 10 to the 6 meters. That's how we define the synoptic scale. The vertical scale, I've written as 10 to the 4 meters. What I mean there is that the 700 millibar, 300 millibar, the fields are consistent with each other. They don't look dramatically different. They differ in the scale of the size of the features, but not in their horizontal extent. And they're lined up coherently in the vertical. So that's the kind of depth of the troposphere. If you went to 20,000 meters or 30,000 meters, you would start to see a difference. You'd be in the stratosphere by then, and these synoptic scales would get smoothed out. The time scale, that's a day. 10 to the 5 seconds is around a day. Again, that's a synoptic scale. Typical horizontal wind over these scales are about 10 meters a second. I know we have jet streams that are much stronger, but they're also not synoptic scale. Typical vertical wind around a centimeter a second. Pressure around 10 to the 5 pascals, that's 1,000 millibars. Typical pressure excursion in the horizontal of about 30 millibars, 3,000 pascals. In other words, highs and lows, 970 to 1,030, something like that. The surface air density is around 1 kilogram per meter cubed. Radius of the Earth is around 10 to the 7 meters, and the Earth's rotation rate is about 10 to the minus 4 per second. They're just constants, basically. Well, surface air density isn't a constant, the other two are. So, we apply those, so there they all are again in grey. So we look at this equation. This is the vertical momentum equation. What happens if we look at the terms in this vertical momentum equation for the synoptic scale? And we proceed in this fashion. We look at this term. So this is dw by dt. It's the rate of change of vertical velocity. So to get a handle on that, the typical vertical velocities we're talking about are a centimetre a second. So the wind can be positive or negative. So it can go up. So it'll vary between, say, 1 and -1 centimetre a second. That's what that means. That's the kind of variation. But over what sort of time scale will that variation happen? Well, it'll happen over something like this time scale of 10 to the 5 seconds. So these undulations, if you like, in vertical velocity will occur over a time scale of about 10 to the 5 seconds. So the gradient of that, the typical value of the gradient, is simply going to be the size of the undulations divided by the period, the time over which those undulations appear. So that's the idea of saying that you replace this derivative here by which this is a material derivative, but so it follows an air parcel, but it doesn't really matter whether it follows an air parcel or is local. These two things are pretty much the same. The Lagrangian and Eulerian will give you a similar answer, is what I mean. And so we have W over T, and so we get something like 10 to the -7. These are meters per square second. G, of course, is 10. And this term here, okay, pressure dP by dz, so we're talking about difference in pressure of around the whole pressure in 10 kilometers. So we're talking about something like pressure divided by the depth. Rho, typical value of rho is 1, so we don't have a problem with that. So it's basically the pressure divided by the depth, so 10 to the 5 divided by 10 to the 4, so we get again a value of about 10. And these things on the right, I won't go through them again, but you get these values of 10 to the -5, 10 to the -3. So what's pretty obvious in that equation is that you have two totally dominant terms. These two terms here are 4 orders of magnitude larger than that one, which is the next biggest. And so clearly, those two terms have to be closely in balance. If the vertical accelerations on this scale are as small as that, then these two terms have to be in balance. And of course, that they are. If you write this balance out, so the pressure gradient and gravitational accelerations are much bigger than the other terms, and they must be closely in balance. So those two terms must balance, and they give you this familiar equation. This is the hydrostatic equation. This is what we derived in the first lecture, only in the first lecture I considered it to be a static column of air. The air didn't move. Now I'm allowing for the air to move. I'm looking at it from a dynamical perspective, but still I get to the same place because the vertical accelerations are so small. The vertical motions in the atmosphere are so small. In fact, this hydrostatic equation is followed on practically all scales of interest in the atmosphere, not just the synoptic scale. You have to go to very small scales or very, very vigorous thunderstorms, and you only get small local violations of this, even in thunderstorms like that. So you do get departures from hydrostatic balance, but very, very small ones. Now, in the horizontal, it's slightly different. So this is the same thing now for the horizontal momentum equation. And the same idea, so we're looking at U, which can be obviously the wind can go positive or negative. And so we're looking at typical excursions of the wind of about 10 meters a second over a time period of 10 to the 5 seconds. So a typical value of the gradient of the acceleration would be around 10 to the minus 4 meters per second. Now, when we look at the terms in this equation, this one, grad p, which is again 1 over rho is 1, this is the horizontal. We're not looking at the whole pressure here. These are horizontal excursions, which are of the order of 30 millibars, divided by L times rho. So we're getting values of about 10 to the minus 3. And similarly again, F is 10 to the minus 4, U is 10. So we get about 10 to the minus 3 here. This one, 10 to the minus 5, 100 times smaller, is negligible given the scaling. But you can see straight away that although you have two leading terms again, these two terms, it's clear that this term here is not so negligible. It's only 1 order of magnitude smaller. And so this balance is not as firmly followed as hydrostatic balance. Nonetheless, it forms the basis of our understanding of atmospheric dynamics, because as we shall see later in the course, geostrophic balance is a kind of sort of neutral state. It's a state where nothing is happening. And it's departures from geostrophy, actually, that cause the structures that we're familiar with in the atmosphere, the growth of cyclones and things like that. Still, we've got to understand geostrophy before we've got to be able to walk before we run. And so what do? Well, these are these two leading terms. So this is the pressure gradient term here, minus 1 over grad p, and this is the Coriolis term, minus Fk cross U. So clearly they are equal to each other. We usually use this balance by defining a thing called a geostrophic wind. So a geostrophic wind is a theoretical construction, and we get it like as follows. This is this equation here, again written down, so that's taken over to the other side of the equation. Fk cross U is G, so we define UG. UG is the wind that exactly balances the pressure gradient. So whereas this is a balance throwing away the other terms, this is a definition of the geostrophic wind. And because K crossed with itself gives you, K cross K gives you minus 1, K cross UG rather. So K cross UG turns the vector through 90 degrees, cross it again, K cross K again, another 90 degrees, and obviously it goes backwards. So essentially, K cross K gives you minus 1, so cancelling out that minus, UG is 1 over F rho K cross grad P. So that's the expression for this geostrophic wind. The cross product again tells you, the K cross product tells you that it's at 90 degrees to the pressure gradient. So here's what I mean here. These are isobars. Here's the pressure gradient going from low to high pressure, grad P, and therefore this K cross grad P, right hand, K is upwards, grad P is that way, and so the geostrophic wind is along the isobars in that direction, balancing the pressure gradient acceleration, which is to the left, the Coriolis, which is to the right. So that's the idea of geostrophic wind then, and then as we've seen, it's fairly closely obeyed actually in most circumstances. So when you look at a chart away from the surface, that's what it looks like. Just a little point about directions. So in the northern hemisphere, the flow around a low pressure is anti-clockwise. So this chart doesn't reproduce particularly well. So here's a low pressure here. So basically the flow goes this way, anti-clockwise like this, around a low pressure, and similarly it will go in a, there aren't any really substantial high pressures here, but it'll go in the other direction clockwise around a high pressure. If you're in the southern hemisphere, this is a weather map from Australia, it's the other way around. So these winds are westerly, the prevailing winds in the southern hemisphere are the same, they're westerly, but this time around anti-clockwise around a high. So in the southern hemisphere this direction is reversed, so you just need to know that. It's actually quite difficult for somebody trained in meteorology in one hemisphere to look at charts from the other one, because you have to kind of reverse your brain to figure out which way the winds go. So we have problems reading Australian weather charts, and they have problems reading ours. But yeah, so anti-clockwise around a low pressure in the northern hemisphere is cyclonic. So I'll be using the terms cyclonic and anticyclonic for going round a low pressure or a high pressure. Doesn't matter which hemisphere, it's still anticyclonic going round a high pressure in the southern hemisphere. It just goes round the other way. Okay. Yeah? So that's the idea of geostrophy. It comes from a balance. It doesn't look as though the scale analysis is particularly rigorous, but as we saw from the chart early on, the flow does actually look geostrophic most of the time. Near the ground, that is not the case. If we look at winds, particularly over land, they don't look geostrophic at all. And the reason for this is friction. So if we include friction in our equation, so now we have three forces, and in order to balance three vector forces, we have a triangle of forces. So this is how so pressure gradient, Coriolis and friction must balance each other in that vector form. And to do that, rather than flowing along the isobars, we see that the wind has to point towards the low pressure. The pressure gradient acceleration is always in that direction because it's determined by the isobars, but friction, which goes backwards, and Coriolis, which goes to the right, obviously vary with the direction of the wind. And so you get this, in order to get this triangle to balance, given that this one is fixed in space, these two have to adjust. And so what you get obviously is a weaker wind. Friction reduces the wind speed, but it also can make the direction of the wind completely different. And over land, near the surface, the wind direction, particularly the wind strength, is very, very different to geostrophic. So much so, in fact, that it's said that if you stand with your back to the wind, okay, if you stand on a day when there are lots of fluffy white clouds around and a brisk breeze, you stand with your back to the wind, so you're pointing in that direction. As you go up through the boundary layer, the friction gets less and less and less, and the wind, as you go up through the boundary layer, rotates and closer to the geostrophic. So what you'd be aware of then, the clouds, which are up in the upper part of the boundary layer, the clouds will be tending to move along these grey lines. So if you stand with your back to the wind, what you'll see is clouds crossing your field of vision from left to right, and you can quite easily see that feature on those sorts of days. It's probably not a good day to try today because it's not really convective today. Over land, then, friction is very dominant near the surface. Its effect reduces through the boundary layer, and above the boundary layer, effectively, it doesn't affect the flow at all. So there is no friction. Friction is basically due to the land surface, and doesn't affect the free troposphere above the boundary layer. It really only has a big effect on the surface layer, but its effect is transmitted to some extent through the boundary layer. It's much, much larger over land than over ocean. That's not perhaps that surprising. Obviously, the land produces, there are bigger features over land than in the ocean, and of course you've got things like vegetation and buildings and stuff like this, which present an obstacle to the flow, which you don't have so much over the ocean. Winds at sea then are stronger, and they tend to be aligned more along the isobars. So if you've ever been out sailing, you'll be well aware of the fact that what can be a quite gentle breeze when you're sitting at the shore can turn out to be a fairly stiff breeze once you get out in your boat. How many of you sail? Any of you sail? No sailors here? Okay. All right, no sailors, fair enough. Right, now I want to turn to the reason that we present upper level charts as the height of a pressure surface rather than the pressure on a constant height surface. And the basic reason is that we can eliminate density from the momentum equation. We do this essentially by taking advantage of the hydrostatic equation. Remember, the hydrostatic equation is so closely followed in the atmosphere that essentially it serves as a constraint for the dynamics. It's always followed. And so what this derivation does is it starts off with a mathematical identity. This is a mathematical expression that applies to any variables, any set of three variables where the pressure, for instance, is a function of height and x. So if P is a function of z and x, then this triplet applies. It's a mathematical identity. So what you see is that P of P is there, there, and there, x, there, there, and there, and z similarly in the three positions. So the whole thing it cycles between the three variables. If I express that slightly differently, I just move these two over to the other side. So the P dx at constant z, that would be the pressure, the gradient of pressure on a constant height surface. So if you had a surface of constant height, that would give you the gradient of pressure is equal to minus, there's the minus there. This one just inverts. Another piece of standard mathematical theory is that if you 1 over one of these, you just turn it upside down. So turn both of these upside down. And what we have is the P dz here at constant x, dz dx at constant P. So this is the P dz, well, this is our hydrostatic equation again. So that's just minus rho g. Lines disappears and we end up with a rho g. So that's easy enough. This one is what I've been basically showing you during the lectures. This is the height, the gradient in the height of a pressure surface. So the P means that the line and the P simply means I'm keeping those variables constant. So at constant pressure, the height, so that's what the charts are showing you, is height of a 300 millibar surface. And if you can visualize that from the charts I've been showing you, you can visualize a gradient in the height of that surface. Yeah? So that's how this comes about, and that's why it's used. Because when you then go into this pressure gradient term, 1 over rho rad P, so this subscript here means gradient at constant Z and gradient at constant P. I don't generally use these subscripts, but here there's a possibility of confusion, and so I put these subscripts in here. So that's just telling you which variable is being kept constant. This is the version that we've had up till now, the gradient of pressure. And we can see that this gives us g times the gradient in z. So now, rather than rho, which is a variable, varies in quite rapidly in the vertical, we have g, which doesn't vary all that much. So we've now got a much more close to being a constant here, times the gradient in the height. So we can then substitute that into the momentum equation. And so here we start off with the horizontal momentum equation that we had before. Okay, this is acceleration, pressure gradient, and Coriolis. And now we replace the pressure gradient by this term here, minus g grad z. So that term there becomes this term here. And the geostrophic wind, similarly from that expression, becomes your over k cross grad p of z. And that's, so the why is this a step forward? Well, because if you try to estimate geostrophic wind from a pressure from a pressure chart, you would have to take account of the density. Here, you just need to take account of gravity. Gravity doesn't vary an awful lot. In fact, it's pretty close to 10 most of the time. We just don't go very high. It varies, of course, by the inverse square law. So if you went hundreds of kilometres away from the surface, it would start to change. But we don't. We're only going about 10 kilometres. And the radius of the Earth is 6,400 kilometres. So g doesn't vary very much. It still varies enough to be a nuisance. It varies according to the inverse square law. So we could define a thing called the geopotential. So this is just potential energy, basically. It's integral of g in the vertical. So the potential energy gain per unit mass lifting a body from 0 to z. And geopotential can then be broken down into a geopotential height by using a standard value of g. You see this little trick? You get a committee to define g. So where's that number come from? Well, it comes from a committee. Okay. And so we can formally remove any variation in g by redefining z. Right? So we define something called a geopotential height. So geopotential height has the same dimensions as ordinary geometric height, is what we would call height. In other words, it's what you measure with a ruler or a laser. This is a kind of fictitious height, but its great advantage is that we can say, well, we can replace gz with g naught h, and then obviously g naught being a true constant can go in there, and we can talk about gradient of the geopotential. So we end up with these expressions here, minus grad phi minus fk cross u. In practice, for meteorology, the difference between geometric height and geopotential height is negligible. It doesn't make any difference, except to certain people, like me unfortunately, who shines laser and radar beams up into the atmosphere and measure the return from the atmosphere and measure height. Obviously that measures geometric height. If you measure the time taken for a laser pulse to go up in the atmosphere and be scattered off a cloud and come back again, that's obviously going to give you the distance, the proper distance. And we do have to put small corrections into our heights in order to compare, for example, with some of these meteorological features. In the troposphere, they are about 100 meters at most. You only get really large differences when you get up to around 80 to 100 kilometers and beyond. So I won't be over-egging this in future. I shall continue to use z as a vertical coordinate, but it will be implicit that that means geopotential height rather than geometric height. It's a level of confusion that helps when you're writing a model, because you don't have to then bother with allowing g to vary at all. You just let it be constant. But the price you pay then is that you have to be ready to interpret this geopotential height slightly differently from time to time. Fortunately, it's not something that matters too much in practice. Okay, so this is where we end up with our momentum equation. So now it looks a lot simpler. We have acceleration is minus the gradient of the geopotential minus fk cross u. This is the Coriolis term, and this is our geopotential. And we can see, sorry, this is the geostrophic wind minus 1 on fk cross gram phi, and that's the easiest form to remember the geostrophic wind in. Okay, so any questions on that? I think I've finished actually, so there you go, we can finish at this point. Any questions? So we've got to geostrophy. Okay, good. Let's stop there then. Which of you has the clicker thing? Have you all scanned the... Okay, good.
Hello. I have a question about how you get the 2 omega cross V from the transformer.
Hang on, I've got my glasses on.
Where?
This one?
Yeah.
Okay, so you've got an omega cross that, and then omega cross V, so that's V there, yeah?
Yeah.
Yeah, you're right, there's a typo. That should be the other side. Well spotted. Okay. Yep, you're quite right. Let me show you what I did wrong. Yeah. So now you have omega cross that and omega cross that times V. So that's V here, the ambiguity. Oh yeah, that's completely silly, isn't it? I've ready to. That shouldn't have a that in there either, should it? I don't know why I've done that. Yeah. Okay. So now Okay, omega cross d by dt and omega cross d by dt of r gives you v, yeah? So omega cross v, then omega cross r gives you that. So, yep, sorry about that.
Okay.
You're quite right, there's a mistake. I'll correct that and put it on the screen. Sorry, that's what happens when you type things.
I get confused.
Yeah, no, right, you're right to be confused. Thanks for that.
我那不知道，没看它肯定要大写。
不用逗号回就好了，还是要逗号？那就
这应该影响不大。你在干嘛？画英语。你还有课在后面吗？
没有，有那个微生物。
哦。所以今晚那事情就取消了。
取消了。会去你们的，但是这样子，那个因为我们要晚上开一个 rap 会，新 rap 会，然后我们是打算在那吃，就是大家各自吃饭，
吃完饭再去那边
聚的，因为我们那边提供餐食那些，还会因为那个点钟的嘛，把我们滞留在那，肯定要提供给中流的。
那么你知道我的 EF2里面有在开始？
知道。等一下，我发完这个邮件给你看。
OK， 我很好奇，谁不是？上一节课的讲义。
对啊。
老师他刚才问我这个写作的意思。
这个。
看过。
这是什么东西？
写错了，把这个 R 划掉，这个 R 里面的括号外面，或者算出来是错，算不出来的。R 是没有的。
就是反正括号里面的都是算式。
对，然后再把这个 R 划掉，后面几个 R 在外面。
这是个。
上来。狗屎！我他妈说半天。
好像我陈家南。但是我不太懂，因为也有华人的名字，我看一下，陈家南，然后老人，我不太明白，我们3个人竞选了，然后我们3个人都在这个名单里，所以我跟老何准备下井。退水，
我操！
要单干，然后这个感觉也是黄丽莎，我觉得很像中国人的。不是，他是 postgrad， 他是 postgrad。
你投票的时候
有4个人嘛，他们好像只有2个。我再看一下，陈家南有一个。
对，我看。
然后，你看有2个，这个是袁谦。
哦，对，好像就是那个烟翠。
对，反正我知道这个。
为什么你个老人？
哦，刘宇，不是，这个也不是，这个是 postgrad。他们就2个，但我们只有3个人，我也觉得很奇怪。我们只有3个人。他们是4个人，然后最后2个人当上了， 我们这3个人竞选，他们学弟学妹也榜单我们3个人的名单。
退市。
但是我们打算退市。
他烟是和烟是两种可以吗？
交流吗？
对。
今天晚上就能见面了呀。
陈家南，他妈真他妈这样个，我操！